Let's pray. Lord Heavenly Father, we come before you this morning with hearts full of gratitude for the protection that you have given to us throughout the whole night, Father. Thank you, Father, for this gift that we can still wake up today morning and still study, Father in heaven. Father, thank you for everyone here. Thank you for teacher, Lord. Father, even as we are going to study, we call for your presence to be with us, Father. And even as we are going to go through the day, we call for your guidance through it, Father in heaven. Give us understanding and give our teacher the words that can simplify things for us, Father, so that we understand quick, Father. It's my humble prayer in Jesus' mighty name I pray. Amen.
Amen. Thank you so much, Ayo, for the word of prayer. Good morning, everyone. Thank you so much for joining. We are continuing with our uh, graphical interpretation and analysis and sketching. Yesterday, we had an introduction where we looked at things such as the asymptote. We looked at things such as the domain. Sorry, we didn't look at the domain, but we looked at things like intercepts. And today we are going to build from there. Now, all those things we are looking at, those are the different features of curves that when they are looking at the graphical work you have done, those are the things they look out for. Does the intercept is there an intercept? That yes. Does this person have the asymptote lines? That yes. Does this person have the turning points? Yes. And now we are going to look out for other features that we need when we are coming up with a curve. And today, our major area of concentration is going to be concavity. Now, when we look at concave, or what we call concavity, we are going to look at those areas where our curve is either increasing or decreasing. Earlier on, when we are starting differentiation, I told you that differentiation mainly looks at the rate of change of something. Now, when you look at our curve, you can note that when you draw a tangent at different points, you'll note that when your gradient, this is your gradient, when you look at this gradient here, when you look at the gradient at that point, you are noticing that our gradient keeps on changing at different points along the line. At this point, you notice that the gradient is negative. In other words, when you try to get your slope, you'll find that the slope you are going to get is going to be a negative slope, meaning that here the gradient is decreasing. There is a decrease. At this point, we know that when it is flat, it is 0. Then you know that at this point here, our gradient is increasing. Now, the graphs we are going to be looking at, we have to identify at what interval is our graph decreasing, at what interval is the graph increasing. When you look at this is what we call a decrease. Now, on your graphs that we are going to have, we need to look at what rate is the graph increasing and what interval is that. That if I have a graph of this nature, then I'll know that from this point up to this point, my graph is increasing. Now, this is what we call an interval. Then I know that from this side up to here, my graph is decreasing. But because you don't know where the graph is coming from, this is what we call negative infinity. Like when you have your number line, when you draw an arrow this side, it means this is going to positive infinity, and then this side goes to negative infinity. Now, when our curve is coming from this side, it means that we are coming from negative infinity up to a point here. So here it means that your interval is from negative infinity up to the point we have here. In case I'm going this side, therefore I will know that my curve is starting from this point, but I don't know up to what point does the curve stop. And therefore this side we shall say it is positive infinity. Now we are going to be looking out for those different parts. Then we are also going to look out for what we call the point of inflection. Now, the point, we have three things I want you to take note of. I've showed you what we call an increase, I've showed you what we call a decrease, and then we have what we call a point of inflection. Eh. Now, this is the British English, but in case you are reading some books and you find something like this, a point of inflection, this is American style. If you find this, it is still correct, but this is American, but since we are colonized by British, then we shall always use the word inflection. But in case you are reading any textbook and you find inflection, it means the same. And when we talk about that, inflection is the point where you curve, where the point between increasing and decreasing. Like when you look here, I want you to tell me in the chart, I have this is point A, point B, this is point C, and this is point D. At what point do you notice which point is between increasing and decreasing? A, increasing and decreasing, or vice versa, such that we identify our point of inflection. Very good. Aha. Very good. Very good. Now that point where you curve either goes up or down is what we call a point of inflection. So looking at our curve, you notice that at this point, this is decreasing, increasing. Now this point in between, we call it the point of inflection. Even this point here, this is increasing, this is decreasing. So this point here, we call it the inflection. And those points are the ones that determine whether your curve is going to concave downwards or to concave upwards. Yes, they determine. And how do they determine? It will depend on how your rate of change, how your rate is it will depend on the rate of change of the function for the first derivative. So this is what we are going to basically look at, such that we know which nature of curve are we coming up with. And you are going to notice that whenever you get a negative will mean that when you are obtaining your derivatives, let me say we have our function f of x is equal to x squared plus 2. When we get our first derivative of x and we get our 2x, it means that for you to get up a negative, it means that to get this, to get a negative, it means that your first derivative, for you to get like a decrease in the slope, it means that your first derivative is going to be a negative. For you to get a positive or to get an increase, it means that your first derivative is going to be increasing. All right. So let me hope you are picking something, and I'm going to ask you to take note. Take note from this side, something from here. You can pick something. But whenever we talk about concavity, we are describing the shape of the function. How is it changing at different intervals? Okay, let me pick on Bettina. Yes, Bettina.
Good morning, sir.
Morning.
It's my inquiry is how different is a point of inflection from a turning point?
Oh, the difference between a turning point and a point of inflection. Okay, okay. Let me talk about it. Hmm. Okay. Now, when we talk about a turning point, a turning point, allow me to use a graph. Okay, let me use this. A turning point is that is one is like we call it the maximum or the minimum point. Like here, this is our minimum, and then this is our maximum. Now, when I talk about a point of inflection, we are looking at the change of a sign. When we are looking about inflection, we are looking at the change of a sign. When I talk about a change of sign, that is what we call a inflection. But when I talk about a turning point, I'm looking at the maximum and the minimum point. Take an example. I may have a graph of this nature. I've given you such a graph. When you look at this graph here, this one is the turning point. This one is the turning point. This one is the turning what? A turning point. But if I'm to read out the point of inflection, I only look at those points where the curve is changing the signs from increasing to decreasing. So a turning point, we look at mainly the gradient, how the gradient changes from positive to negative. However, when I'm talking about inflection, the gradient, okay, I will show, we are going to look at a graph. We are going to look at a graph whereby there is a change of sign, but there is no turning point. We are going to look at a graph at a later time. But when it comes to inflection, we are looking at the changes in the signs. We are looking at the change in the sign, how the gradient changes from positive to negative. And for it, it is not just a point. For it is like a region, or like an interval. So it's not that it is only specified at this point, because at this point here and here, we can say that there are going to be a change in a sign. So it's not, for it, it's not a point, whereas the turning point is just that is I want to say that for it is a point, but this one, when it comes to inflection, even it can be within a given range, where you notice a change. Then maybe even another difference could be that turning points are stationary, in that the slope is zero at that particular point. But when it comes to inflection, it does not mean that there are zeros. For it can either be zero or it can still be a non-stationary one. Though sometimes they can be the same. Sometimes they can be the same. Okay, maybe I don't know that I need to, Bettina, we are together, but I can give you another graph, hoping people are writing. Maybe if I give you this graph here, let me show you this graph like this. When you look at this graph here, this graph has a point where like it turns from. But when you look at the gradient, here, the gradient is going like this. The gradient is going like this. So you may have such a graph which has a point where it is turning from, but it doesn't have a point of inflection. Hope, I don't know that is clear now. Hey. This point, when I have a curve of this nature, you can notice that there is a turning point here. The curve comes and then it turns up. Here, the gradient is increasing. The gradient is increasing. But since there is no change in the sign of the gradient, then this one doesn't have a point of inflection. Inflection, we look at in between increasing and decreasing. Then a turning point, we just look at that point where your curve turns to either get a maximum or to get a minimum point. I don't know whether Bettina, you have got the difference.
Yes, teacher, I've got it.
Okay. Free boss.
Sir,
Yes.
I've not understood anything. I've just joined, so I don't know if I can repeat from me from where I started from.
Okay. Unfortunately, I will ask that you are going to follow up. You'll pick from there in the process, because now, so far, 16 minutes, so there is a lot we have been able to cover. So I may not be able to go through everything, but you pay attention going forward from what we are going to look at. But what we are looking at is increasing and decreasing and the concavity. So those are the things we are looking at. And at the moment, members are taking some few notes from here. But I'm going to keep on explaining in the process.
So, where is it applicable in day-to-day life?
One, which subjects do you do? What's your
I,
combination?
I do have.
Head, yeah? Oh, okay. Okay. Now in life, take an example. Uh, when it comes to reading, uh, let me draw a curve of this nature. We have what we call a productivity curve. There are points in life where you're going to read and you'll feel you are very productive. Things are entering, and the time is going to reach where you're like, in other words, you will be like this. We shall have a positive gradient. You will feel things are entering, things are increasing. You read, things are entering. And then you reach a maximum point whereby things are okay. Then after some time, you'll feel as if nothing is entering. So your graph will
Yeah,
start
actually, you're right.
decreasing.
Like at this point,
Mhm. So that is where it is applied. And even in economics, we have these productivity curves, and we shall draw some whereby things will first work out for you. Now, like an example, I can use this concave up. There are times in life where you're going to find things are working out for you. Things are just increasing. Every paper you feel you are getting well, you are getting there. And then time is going to come where things start now decreasing, changing. After you have reached the maximum, so we have what we call the maximum productivity. So the maximum productivity here gives us the turning point. But in between this and this, there is a point where you will start feeling things are not working out. Things are not working out. So the inflection region is that region whereby you are saying things here are not working out well, where you start having that kind of feel. Now, these are some of the things. Even those people, when you go to business, we draw graphs in business. Even you have seen when it comes to working, there are some periods, or like there are some sections within the day where you are very productive. You sit down and you are able to do things very well. So that means it is an increase. The rate of working of your product, the productivity and the time, it means it is increasing. Then time comes whereby everything is a bit normal, you don't feel yourself, and then you start decreasing. So that is where it applies in real life. But also when you go to business, you'll find out that some seasons are increasing, things are working out very well. And there is a time whereby, like here, you are getting money is coming in. And then you reach a point where the money you are getting is constant. Maybe 50,000. And then time is going to come where things are going to start dropping. Even in marks, you have seen in some subjects where you have improved from a 50 to a 60 to a 70. Time comes when 80s are your things. Then maybe, God forbid, something happens and then you go back. So that's where these things work in life. Okay, I think members have finished. Yes, I've finished to take note of that. So I have my graph here. Have my graph here. And when you look at this graph, still, I wanted to show you one is where does the curve increase? When you look at this curve, when you draw when you draw a gradient, a line there, and you draw a tangent at this point, you draw a tangent at this point. You notice that when we draw our tangent, here, our gradient, the change of the gradient here is going to be a negative. At this point here, the gradient is going to be a positive. At this point here, it's going to be a negative. That means that for this one, we shall have a point of inflection because there is a decrease and an increase. And a decrease and an increase. So we have a point of inflection, we have a point of inflection. And for this particular one, it is -1, and for this is 2. Then if they ask you, what is the interval for the points that are increasing, interval for the increase? When you look at this curve is coming from somewhere we don't know. And this side, this is what we call negative infinity. And this curve is going somewhere we don't know. We call it the positive infinity. Now, when they ask for the interval of increase, that means that when I'm writing the increasing part, I'll ask myself, where is the increase? Increase is from here up to this point here, between -1 and then the 2. In case I'm looking out for my decrease, then I also check out that my decrease. Now here you take note, in case I'm looking out for the increase is between -1 and then 2. Is that okay, members? Then in case I'm looking out for the decrease is between negative infinity up to when I reach -1. Union between 2 up to positive infinity. This is the region for the decrease. Let me hope members are getting it. Increase is between -1 and 2. Decrease is between negative infinity to -1, union 2 and infinity. Members, have you understood that? How we read the interval from the graphs? Is it clear to everyone? Kindly let me know in the chat. Increase, you look at the positive gradient. Decrease, you look at the negative gradient. Okay, I'm going to have another number. Here you mean I'm going to have another number. I have this one here. This is my graph. So when you draw your tangent along the curve, I will draw a line here. I will draw a line somewhere here. I draw a line here. I draw a line here, like that. So when I look at this, I'm going to ask myself, where do I have a positive gradient? Remember, positive gradient goes like this. That is what we call a positive gradient. When it goes like this, is a negative gradient. When it is flat, the gradient is 0. So here, you note the gradient is positive. So here, I can say that there is an increase. Here, there is an increase. Here, there is an increase. Here, there is a decrease. Now, when you look here, this is a turning point. There is a turning point here. But there is no point of inflection at this point. There is no point of inflection at this point. When you look at here, it is still increase and then increase. So there is no point of inflection. However, between here and here, there is an increase and a decrease. So that means that we have a point of inflection at that point. Now, in case I'm reading out, I want to obtain my region. I want to obtain the region for increase for this particular curve. I'll say for increase, this side is from negative infinity. I told that this side, it means negative infinity. This side is positive infinity. So it's from negative infinity to, hope you are noticing, it goes up to -1, it's still increase. 2 is increase up to 5. Then from 5 going this side, it is a decrease. So when I'm reading up the decrease, it means I will start from 5 and then I go up to positive infinity. So now that is how we read out the interval, whether your curve is increasing or decreasing. Are we together, members? Is that fine? Okay, okay, okay. I'm going to have one that I want you to try out for me. So I'm going to ask you for this one, what are the intervals of increasing and decreasing for the curve? As I pick on Gilbert. Yes, Gilbert.
Good morning, sir.
Morning.
My question is on if you can slightly put on the previous curve
Hmm.
and the way you see the interval, like the one of increase.
Hmm.
When we are stating, do you break it like the other first one where we put in the union, or for it we just mention from negative infinity up to 5?
Yeah, that is very okay
Okay, sir.
because there's no decrease.
Okay.
Okay. Okay. Yes, Mark.
So I was requesting if you could give us one more example so that I could try getting it better. I don't know if it can be possible.
Okay.
Yeah.
Uh, Esther.
Okay, teacher, me, I've just failed to understand. Like, I was confused on the point where you said it was inflection. Because to me, it looked like a maximum.
Like I've said, I repeat, I say that when we talk about inflection and the maximum, it is okay. But what I wanted to bring to your attention that when we are mentioning a point of inflection, we are looking at the change in the gradient between an increase and decrease. A turning point can be anywhere, but it can be at a point where there is no point of inflection. And I gave you an example that you can have a graph of this nature. At this point, our graph is turning. But since the gradient here is positive and here it is positive, this one is not a point of inflection, much as it is a turning point. Are you getting the
Teacher,
difference?
yes, teacher.
But if you have a graph of this nature, here the curve is increasing, here the curve is decreasing, but it is turning. So this one, between increase and decrease, there is a point of inflection, but at the same time, there is a turning point at that point.
Yes, teacher, I've got it.
Okay. So I repeat for those as others are trying out. I said that what matters a lot is you knowing what is that point of increase and decrease. You come to your graph, look at the shape of your graph. I can draw a tangent here. I can draw another tangent here. I can draw another tangent there. When you look at all those tangents, you notice that for this line, you need to know now the nature of a positive gradient. This is what we call a positive gradient. Even if you try to draw a line like this, you know that your gradient, the change in y, the change in x, for this particular one, it will be, let me say roughly, between 3 minus negative 3 divided by, here let me say this is negative 0.5 and maybe this is negative 1.5. Then you know that here I'm going to have my gradient between negative 0.5 minus negative 1.5. So you end up with something like 6 out of negative 0.5 plus 1.5, which is a 1. So you end up with a 6. Now that means that the gradient is positive. So the moment your line is like this, it means it's a positive. And a positive means that there is an increase in the rate of change. Here it means that there is a decrease in the rate of change. Now, whenever you have between a change of sign from increase to decrease, then there exists a point of inflection. And that point, you just look at the maximum point, you read it off. In case you have between increase and decrease, as long as your gradient changes, then that means there exists a point of inflection. Yeah, let me hope you have understood that. So here I was asking, what are the intervals for increase and then decrease? So I want to look through the chart and I see what people have put. Increase, someone has given from negative infinity to 0. Union from 2 to infinity. Very good. Decrease between 0 and 2. I agree with you. Let me hope members now are getting that. Infinity, yes. Swabla, Gilbert. Hmm. Okay. Okay. Yield stands for union. Okay, let me give you another one to try out as well. So here, you notice that from this side is negative infinity up to this point, which is 0. And then from here up, where? Increasing. Then from here, going this side. So this is from 2 to positive infinity. That's why we have an increase. So increase, you combine the two regions, negative infinity to 0 and 2 to infinity. Then decrease, it is in between these two here. So it is between 0 and then that 2. Okay. 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 I'm looking through the chat. I'm looking through the chat. Okay, okay. Yeah, okay, I've seen. Okay, okay. So, okay, now I'm going to throw some light. I've seen some question in the chat between two things that I want to bring to your attention. There is a difference between what we call a point of inflection, what we are talking about, a point of inflection, and what we call a stationary and what we call a stationary inflection point. I want to bring it to your attention. I want to repeat that when I talk about a point of inflection, I'm looking at that point where our curve changes from increase to decrease. That is very okay. Take an example. When you look at this curve here, there is a decrease. Here, there is what? An increase. Now, even that point, maybe I'm going to draw for you a curve. That point may even just be anywhere, may not even be specifically here. But as long as within that region that you have taken on, has the curve is changing from increase to decrease. Even it can be around here. However, when it comes to stationary inflection point, now stationary, like you hear the stationary, it means that at that point, your gradient for the first derivative is equal to 0. I don't know that people are getting the difference. It means that at that point, your gradient for the first derivative is equal to 0. So if you have curves of this nature, let me say you have something like that, and you find out that there is a point here, like I use this graph here. I told that for this graph, since this one is increasing and here there is increase, here we cannot say that we have a point of inflection. But if your graph looks like something like this, then here I can say that here your gradient will go like this. Here your gradient will go like that. Now I don't know why Freebos you are writing on our screen. Okay, let me first disable him. So I'm saying that if you have your graph and your graph is like this, you have to look at your graphs very well, like this. Now don't cram, because now when you look at this graph, you look at the gradient will be like this, and here the gradient will be like this. So you notice that here there is a negative, here there is a positive. So that means that there is a point of inflection that can happen around there. But if you are looking for the stationary point of inflection, then at that particular point, it means that the gradient must equal to 0. So you look at that point of your function where your gradient is equal to 0 specifically. That is the stationary point of inflection. But a point of inflection even may be any point as long as within that region your graph is changing is between increase and decrease. I don't know whether the person who was asking, you got that. When you look at a graph of this, let me say you have looked at a graph of this. I want to bring it like the way I saw it in the chart. Something like this. And there is a point here. When you look at your graph here, it is something like this. Like here, you look at your gradient going like this. You look at your gradient going like this. So you notice that here there is a decrease. This is like a negative gradient, and this is like a positive gradient. But if your graph is like this, something like this, here you cannot tell us, here it is increase, here it is what? Increase. So there is no point. So you look at the graph specifically. Look at that graph. User, don't confuse. The stationary point of inflection is the turning point. Let me take it, bring it like that. There is a difference between stationary point of inflection and a point of inflection. When there is a word stationary, it is very okay to say it is the same as a turning point. But if it's just a point of inflection, that means that point, any point between the increase and the decrease. It does not specifically need to be a turning point. Members, are we together on that? Have you got the difference? The person who asked, I think it was Fikja. I don't know whether you have got the difference between the two. Yes, Samsung.
Good morning, sir.
Morning.
That means if the stationary point is the turning point for this curve where there is 1, when the curve is increasing at the same after it decreases. Here where there is 1, that means it is the stationary point because it's the turning point, though it's not the point of inflection.
Yes, this one now we can take. This is the stationary point of inflection. It is okay. Yeah.
Okay.
But any point along here, in case now they ask for the point of inflection, it can be along any point along here, as long as your curve is increasing and decreasing. So someone may give us, let me say 1.1, 1.2, as long as you see that what? That difference. Okay.
Excuse me, sir.
Yes.
Now, can't the point of inflection, though the curve will be changing from negative to positive, at the same time be the turning point of that curve?
It is possible. It is possible.
Okay.
Okay. Then the last one is here. The last one is here. State for me the intervals for increasing and then decreasing. State in the chat. State. And when you see these graphs show you that they are coming from somewhere, not that they start from here. So that's why we say always, this is negative infinity and this is positive infinity. And be careful with the brackets you use. Don't just use any brackets for you wish to use. In case it is negative, when you use such a bracket, this bracket here shows you that it is not, whatever you have put inside is not inclusive. Take an example. It shows that negative infinity up to -3. That is the meaning. So negative infinity is not part, -3 is not part. When I say now I'm looking at increase, union, it means that another interval that increases is between -1 and then 1. That is the meaning. Don't use these brackets here. These brackets mean inclusivity, that whatever you are putting in, it is part of the solution. That's the meaning. But here we are stating the interval between what and what. Now, Shad, I've not understood your question. Moses, I'm worried. Your answer? Yes, Jimmy?
Master, you say that when we are writing the interval, we use these brackets that you've written here on the screen indicate that show that it is exclusive.
It
Now,
is?
what if you said that they show that whatever inside is exclusive. Now, I want to write, like, for instance, that the interval for increase. Now, will I write them inside? Now, how will I write it there?
I have given you an example. Are you seeing what I've written?
Yes.
This is the interval for the increase.
Yes. You've said that
I
whatever
have said, don't use these ones here. When we talk about interval, we are looking at, like, within which region does something lie, but not limited to. Like what I'm telling you, if you put, let me say you put 1, -1 and 1, it means that here, where is 1? 1 is here. your increase is between just 0, is between 0 and 1, not necessarily that it will, because at 1 you are not seeing that there is a change, that it is also decreasing. So you cannot include 1. I don't know that you're getting it. Because 1 is like a turning point. It can either increase or decrease. So you cannot use these brackets. So that's why we exclude it.
Okay.
But our interval reaches there. I don't know that you're getting the difference.
Okay, master.
When you look at 1, here you are not saying that 1 is a turning point. Here, 1 is between decrease and increase. So since you don't want, you are not sure, is it increasing or decreasing? It is in between there. So that's why we use these brackets to show that 1. But what I'm saying, don't use this one. The moment you say this one, it means that you are sure it is increasing. Yet at that same point, it is decreasing. In simple terms, don't include the turning points.
Okay, sir.
Okay. 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 At least I've seen the answers. Dorcas, yeah? Okay. Okay. I'm saying those answers are okay. Those answers are okay. So we are going to continue. So here for decrease, I expect you for decrease to have between -3 and then -1. Then you tell us -3, comma, -1, union, and another decrease is here between 1 and then positive infinity. So you write it like that. So that is what we call the interval for increase or decrease. Okay, now we are going to look at another concept we call the domain. When we talk about a domain, I'm seeing a hand. Moses, okay, we call the domain. When we talk about a domain, we are looking at the set of all the input values, the set of all x values that can satisfy the function. Any value of x which makes that function valid is what you call the domain. The input values. What do you put inside is what you call the domain. What you feed yourself is what you call the domain. So the domain is a set of all the x values for the function that satisfy it. However, take an example. I know you looked at the domain in your senior 2 when you are looking at functions. If I have a function f of x is equal to x plus 2, members in the chat, tell me what is our domain. Put in the chat what your domain is. I want to see what people. Okay, Moses, it is okay. I wanted people to tell me what is your domain. In your senior 2, you looked at domain. Okay. Okay. Now I'm not saying something. Yeah. But here, when we talk about a domain, we are looking at what x values, which when you put it inside here, make your function work. So when you look here, an x value you put here can work. When you put 1, you can get an answer. When you put 2, it can get. When you put negative, you can get. Now here, when we are talking about the domain, it means that we give all the possible x values. And now here, that's why they tell you a set of real numbers. Here we don't mention things of infinity. Here we mention things concerning real numbers. So when you are stating now such a domain, you will say x contained in the set of real numbers. Real numbers, we refer to those rational numbers, we refer to those integers, whole numbers. Those are what we call real numbers. Yeah. So a set of real numbers. So here, any number you put in will make the function work. That's what we call the domain. So domain, so this is for linear functions. In other words, when you try to graph this function, when you try to, I think, let me now get to the graph such that you can get this concept a bit better. Yeah. The domain, it's going to be you need to understand those concepts. And for those people who are going to go deep into math, understand the only things that we shall eliminate will be those things that give us like square root of a negative, or what we call irrational numbers. Those are the only things we exclude from the domain. Yeah. But any number which when you put in the function, it makes sense, we call it a domain value. But if you've put in any value and it does not make sense, then it's not a domain value. Okay, it is opening. I'm going to draw. So as it opens, I want to give you another one. Imagine I have f of x is equal to 1 out of x minus 1. What is our domain? Now, your domain contains all the values that make sense. Now, if you find that there is any value that does not make a sense, you exclude it from your domain. So what could be our domain for this? X members of all real numbers, but not 1. Perfect. Thank you, Ayob. Yes. So that is what we call the domain. That here, we shall have x contained in all real numbers, apart from when x not equal to 1. Because you notice that when you put in 1 here, you get 1 out of 1 minus 1, which is 1 out of 0, which is infinity. So that is the meaning. So this is where in your O-level, I think they used to use the word, at what point is the function meaningless? At what point is the function where the function does not exist? In other words, that's what the criteria we used. That whenever you have a function, now for these ones that are rational in nature, you always look at the denominator, and that denominator will help you to determine whether that point exists in the domain or it does not exist. Okay, I have my graph here. I wanted to show you. So I'm going to explain two concepts that I want you to understand. These two concepts here. Now one, allow me to draw the graph of y equals to x plus 1. When we talk about a domain, I refer to you look at the x-axis here. Now, any value along the x-axis can qualify to be within a domain. Because you notice that when I put in 1, I am able to get a value. When I put in a 3, I am able to get an output. When I put in 5, I am able. When I put in negative 3, I can. When I put negative 5, I can get a corresponding value for y. Now, those are what we call the domain value. So domain value means the values, all the x values. And those values are what we call the real numbers. Even these values in between the points still qualify to be called real numbers, because real numbers contain any value that is rational, any value that is an integer, any value that is a whole number. Even 0, you can see that it can give you. So when we talk about domain, you look along the x-axis. This is what we call the domain. Another term we call it, okay, before I leave the domain, let me now give you another one. You need to be very, very careful, and you need to understand the concept. If I have something like this, this is, okay, I have y is equal to x squared plus 2, something like this. Still, when you look at this, when you look at my graph, still this one has what? A domain. So here you notice that any x value you put, you can get the y value. You can get the y value. You can get the corresponding y value. So here I can say that the domain can contain all real numbers. However, if I come to this graph I can still go on and say, I want my graph to start from here and end at this point. Now, if they cut off this part here, they remove it, and they remove it, and they're asking for your domain, what do we do, members? I'll come here, I read off the value, I'll come here, I read off the value. So for such a case, our domain is going to be between -2 less than or equal to x less than or equal to 2. Members, are you getting the difference? Are you getting the difference? Okay. Okay. Perfect. Perfect. Cool. Okay. So that is when they have restricted it. Now, number 2, allow me now. When is it meaningless? When it does not make a sense. An example I'll give you for that one to see that where it is meaningless. Allow me to draw the graph y is equal to 1 out of x minus 1. Now, you are seeing that kind of graph. Now here, you notice that at 1, at the point 1, there is no any corresponding value for y for the curve. And here, you notice even down, there is no any corresponding value for the y. And that's what we call the asymptote. So it means that your curve does not touch that point. So that's when we say that at that point, the curve is meaningless. It does not make sense. So now that means that when you are stating your domain, now such a value is excluded. In other words, you exclude your vertical asymptote. So here we shall have the values of all real numbers, and then we shall go on and exclude our 1, because at that point there is no output for that particular value of 1. Hope, Shadow, your question is answered. Okay. Now, allow me to bring in another concept as I talk about domain, because the domain goes hand in hand with what we call, okay, let us first finish the domain, then I'll bring in that other concept. Okay, now when it comes to rational functions that we mainly look at here. So there I was showing you when you have many linear functions and quadratic functions. Now when it comes to the linear function, for you to know your domain, always look at what you have in the denominator and then equate it to 0. Look at what you have in the denominator and then equate it to 0. So I'll first give you some example on that. Take an example. We have our function y is equal to 6x plus 4 divided by 2x plus 1. They may ask you, find the domain. Now here the domain, to get for such a function, look at what you have in the denominator. So what you have in the denominator cannot be equal to 0. Cannot be equal to 0. So what you do, you say 2x plus 1 should not equal to 0, such that you get that value of x that does not yield any output. So you say now 2x should not equal to -1, and therefore x should not equal to -1 out of 2. So that means that x is contained within all real numbers apart from when x is not equal to -1/2. So all other numbers hold apart from this particular number. Hope members have got the difference. In case you want to write it in terms of an interval, you can visualize it like on your number line, whereby this is where you have -1/2. This side you have -infinity, and this side you have what? Infinity. So you can say between -infinity to -1/2, union between -1/2 to +infinity. That's when you want to write it in an interval format. Okay, so that's how you set your domain. The domain gives you the value of x's that are varied for your expression. Members, let me know whether we are on the same page. Okay, Shadow says yes. Ayobo, yes. Okay, yeah. Gilbert. Okay, allow me to give you one number such that you do for me at least one number and you tell me which domain you are obtaining. You tell me which domain you are obtaining. I have here my function. Let me clean the board. And here, make sure members you understand. You understand. Okay, let me give you here. I have my y equals to x squared minus 2x minus 3 out of 4 x minus, let me say, 20, 24. So what is your domain? What is your domain? Okay, that is okay. Remember when you are stating your domain, Bettina, I've showed you how to state your domain. I know 6, all real except x equals to 6. Very good, yes. So all real numbers except when x is equal to, apart from x is equal to 6. Or someone can say negative infinity to 6, union 6 to positive infinity. So that is our domain. Yes, but all real numbers. In some books, depending on the book you are reading, they can even write it in a set notation format, whereby they can write x, then they say x apart from x contained in 2. So in case you find it here, it is also very okay. They can write it in this format depending on which book you are reading. So that is what we call that domain. Now, we look at the second concept. The second concept is what we call the range. When I come to my graph here, I want to draw a graph. We are going to start with the linear graphs. Let me say I have x plus 2. Now, when we talk about a range, we look at the output, what you get, what you like. When in real life, when I talk about a domain, it's like the input. What you put inside yourself is what you call the domain. Now, what happens in real life that if for you yourself, you allow yourself to put everything that comes into your head, it is just a matter of time to show us what you are producing. So what you are producing is what you call the output. And that output mathematically is what you call the range. So if you put, let me say, you put inside your head a lot of things that are useless, with the time, you'll also start having an output that is useless. Garbage in, garbage out. Now, that's why it is always very important to restrict the domain. So when I showed you for the other graph, when I had restricted it, when you restrict yourself within a given interval, it gives you time to reset and to know actually what is important and what's not important in real life. That's why it is always good. Restrict what you put inside yourself. In other words, restrict your domain mathematically. And now the output, it means that when you restrict what you put inside, also your range will be restricted. Now, when we talk about range, we are looking at the output. What is it that you produce? What is it that comes out? Now, when you look at this kind of graph I have, our y values are the ones that we get, like, these are what we call the range. Range is vertically. Horizontally, we obtain the domain. Vertically, we obtain the what? The values. So the corresponding y values, let me say this is our x. This corresponding y value is what we call the range. The corresponding y value here, we call it the what? The range. So you note that if it is for the range, members, can you first try out and tell me, what do you think is going to be our set of values for the range? You put for me in the chat. What do you think is going to be our values for the range? Look at our line. When you look at the line, you are noticing that our line goes up and down continuously. It's not ending. It's not ending because this line is an open line. Even if you try, it will go and it will go. Now, for such a case, it means that all real numbers do qualify. All real numbers. Or you can say between negative infinity to infinity. No, now here, shadow, you don't restrict because if you say from 2 to infinity, it means that for you have started from here and you have gone up. What about these values down? They also contribute. So for such a case, you just say negative infinity to infinity. That is your range. Or you can say all y values contained within a set of real numbers. I don't know whether members are getting the difference. You need to understand now because when we are drawing the curves, we shall need always to look out for some regions. Okay, from there, allow me to remove this graph and I give you this graph here. I have y equals to x squared. Let me start with this graph. When you look here, our graph after drawing, you note that our graph, remember I've told you we read all the values in that format. When you look at our graph starts from this line and our graph is going to go where? Upwards. Now, if I'm looking, when you look at this line here, this line is the line y equals to 0. Now, if I'm looking for the range, I look out for all these y values the curve takes on. It takes on 0, it takes on this one, it takes on all these ones. So for such a case, I will say that my y values for my range are going to be all values greater than or equal to 0 because also 0 is part of it. So any value above 0 or equal to 0, as long as it is a y value, it's going to be varied. Members, are you getting that? Understand now. It is about understanding the concept. Are we on the same page when it comes to this kind of range? I repeat again. When it comes to the range, look out for the vertical movement of the curve. When you look at this curve is curving at this point here. That means that the values, when you have x as your input, you get this value. When you have -2, you get a value here. When you have -3, you get a value here. When it comes this side, you get these values here. You notice that all the y values you are getting are values that are up the x-axis. That means that when I'm stating my range are the y values, are the output you get as a result of putting in the x values. That when you put in 0.1, what do you get? When you put in 0.2, what do you get? So that means that here, our values are all the y values above the x-axis. So for such a case, I will say y should be greater or equal to 0. Because even when I feed in 0, I get 0. Alternatively, someone can say between 0 and positive infinity. Now, that is how we can state our range. I've said you need to understand the concept. Allow me to give you another one. Allow me to give you another one. And when you understand, you are going to allow me to use this. Allow me to put 2. Look at my graph. Can you tell me in the chat, what do you think your range is? What is your range for that particular curve? -2 to infinity. Negative. Thank you. Thank you. Now members are getting it. Yes. So what about when I have that? What about when we have that? What could be our range? So hope members are now getting the what? The difference. So for such a case, we want all these values from 2 onwards. All the values will qualify to be called our range. Between 2 and infinity. All the values that above. So that's how we read our range. Yes, and I know those people who have finished, I know you have looked at some of these things, though I am not sure, but I know you may have looked at them. Now, what about we are now? I was giving you those ones. I expect you must have looked at in senior 2. Yes, in senior 2. Yes, and part of senior 4 maybe. And then now, what if I have this? Now, when you look at the curve I have here, this is my curve. When you look at it, you are going to notice that this curve, can you first tell me which line are you seeing the curve not touching horizontally? Which line is that you are seeing the line is not touching horizontally? Horizontally, remember when now you are reading y values, you read horizontally. People are saying 0. When you look at this line very well, our curve is not touching it at all. What does it mean? It means that any value above this line here is within the range. Any value below this line means that it is within the range. Because you consider both curves, you don't consider one. Now, members, can you first try? You tell me, what do you think our range is going to be? What do you think our range is going to be for such a curve? For such a curve. What do you think our range is going to be? Moses, we are not safe. When you say between negative infinity and infinity, it means you are including in the 0. Is our curve touching that line? So now you need to all real values except 0. So now you need to know that here 0 is not inclusive, because 0, when you have this y line, there is no any value that gives you an output. Now you need to be very, very careful. Allow me to give you another one. Allow me to give you another one. And then we are going to start visualizing it very well. We are going to start visualizing it very well. Take an example. I have y is equal to 2x squared minus 4x plus 5 out over x squared minus 2x plus 1. Sorry. X squared minus 2x plus 1. I have that one now. Look at it. Look at it and tell me, what are you noticing? You first observe that line, that the curve doesn't touch, but it just appears. Look at that, and tell me, what would be your range? This is how our curves are moving. So what do you think is going to be our range? Observe very well the graph. There is a line the graph is not touching, but they appear to be a bit very close, but they don't touch actually. I want you to look here, around here. This line will go and it will go. All values. User, remember, when we are stating the range are y values. Range are y values. Ayobo, that is okay. So for such a case, members, when you look at our graph, you notice that our graph is going upwards. And it is the points that the output starts from 2, 3, 4, and onwards. So for such a case, it means that all values of y that are greater than 2 qualify. So your range here for such a case will be y is greater than 2. Yeah, let me hope, remember, all y apart from, now here you can't say all y apart from 2. It means that also, Jimmy, you are including -1. Is -1, does -1 correspond to anything? That no. You observe your graph very well. So here the only way we can state it can be y greater than 2 or 2 to infinity. Yes. Yeah. And this is going to be very important, very, very important when we are coming up with our graphs. Let me give you another one. Observe, because this one is observing. I repeat, when you are stating the range, don't mention anything like x anywhere. X, only mention it when you are talking about the domain. When you are mentioning anything concerning what? Don't mention it anywhere. Okay. I give you another one here. Look at these graphs very well. I give you another graph. Now look at this graph of mine. Look at that graph of mine. Look at that graph. You tell me, what do you think? What do you think? I know it is a bit there, but I want you to note something. Can you first try? What do you think our domain, sorry, I want the range. The range is going to be. What do you think the range is going to be? Someone has already mentioned that one, you are going to have a point above 3, which is correct. That's one. Thank you, Moses. Then I want you also to look down here. There is another line somewhere here, though I know it's not so clear, but for your range now, it's going to be all these values down and all these y values up. That's going to be your range. And now I want to also now bring in something here you need to know. Now, this region you are seeing here, in those old textbooks, all those books you are reading or you have, it's what they have been calling the region where the curve doesn't lie. Hope that is okay. The region where the curve doesn't lie. So above it is where you have your range. Below it is where the range exists. So I know depending on what you are following, when they ask you for the region where the curve doesn't lie, this is what they are meaning indirectly. Hope now you are understanding, those who have already covered this topic. So when they ask for the range, we expect you to say the values that are above 3, y values, and for this case, you will find out that all y values that are below 3. So your range lies above and then below. That's what I wanted to bring now to your attention. I can give you one more. I don't know whether we're on the same page. May I know whether it is the unwanted region? Not unwanted region, but in that region, there is no curve that lies there. The curve doesn't lie there. So in that particular region, I think they call it the region. The region of restriction. I think that's the word they use. The region of restriction, where the curve doesn't lie. And whenever you are going to draw your graphs now, you will need to know that region. It's going to be very important because in that region there is no graph. There is no graph in that region. We call the region of what? Restriction. So in case now, for those who have already done this, those ones who have already maybe interacted with this topic, when you get that interval where your curve doesn't lie, it will be something like this. So in case you are stating your domain, your range will be the values of y above 3 and then the values of y that are below a third. Okay. So that is what we call the range. Be very careful when we are finding the range. And I don't know whether you need to know that your syllabus emphasizes some of these key things. Allow me to open for you the syllabus a bit, because you need to understand. Do not cram these concepts, because they are going to be very key, because the question can come from around there when they want you to know, to tell them what is your domain and what is the range when you are sketching. Yeah, it is very, very, very important. That's why I'm emphasizing on it, for you to be able to understand those concepts. When you look at your syllabus here, they have emphasized intercepts, they have emphasized asymptotes, range, and domain. That's why I'm talking about them. We have looked at increasing, decreasing, concavity, and turning point. So that's why I'm looking at those particular concepts. Okay, so I'm going to continue, and now I'll show you how do we obtain the range is the next one. But like you said, the syllabus, I have first showed you how we do them using the graphical approach. But now we are going to use the algebra. How do we do them using the real algebra? And now that is where we are going to concentrate. Okay. Now, what happens in case we are using algebra? So, when we talk about range, like I've said, range means the set of all output values, the set of all y values. That is what we mean by a range. Now, how do we obtain the range? There is to get your range, in order for you to be able to get the range, I'm going to show you one or two approaches. But the first one here, we are going to first obtain the domain, and then I will show you how we obtain the range. So allow me to start with the domain and the range. So what am I going to have? I'm going to come here and I say that in order for me to obtain my domain, we say that for the domain, our denominator will equal to 0. So I say to obtain the domain, I'll have my x squared minus 2x plus 1 should not equal to 0. That is the condition. Do not forget it. That denominator should not equal to 0. Now, you are going to solve. So, when you look at that kind of equation, you notice that that kind of equation is the same thing as x minus 1 squared not equal to 0. And therefore, this means that x minus 1 cannot equal to 0, and therefore x cannot equal to 1. That means that your domain will contain all x values. Here, you can say now your domain contains all x values apart from x when is equal to 1. Alternatively, someone can put it in this format: x contained in a case of x not equal to 1. Someone can state it like that. Or someone can state it in form of negative infinity to 1 union 1 to infinity. Something like that. That is the domain. Now, when it comes to the range of the values, you are going to take steps. When we are finding the range, earlier on, you looked at the quadratic equations, and you said that when you have b squared minus 4ac greater or equal to 0, when you have the discriminant should equal to 0. Now, when we are finding the range, we are going to express, since we are looking for the y values, we write the whole of this equation we have in terms of y. And then we use this condition for the discriminant to be able to get that particular value. So what are we going to do? So we are going to do our cross multiplication. such that we form a quadratic equation in this format. So I'll cross multiply. So I'll have y into x squared minus 2x plus 1 equaling to 2x squared minus 4x plus 5. When I open up, I'll have yx squared minus 2xy plus y equaling to 2x squared minus 4x plus 5. So I'll continue and collect like terms because I'm forming a quadratic equation written in terms of y. So I'll have yx squared. Now I'll bring in the x minus 2x squared minus 2xy. I bring in this 4x. It becomes plus 4x plus y minus 5 is equal to 0. May I know whether we are still on the same page? Yeah. Ayobo, where is the negative coming from? There is no negative 1, eh? Remember, x minus 1 means x minus 1, x minus 1. Secondly, you can't have a root of 0. A root of 0 is 0, so you cannot say plus or negative 0. 0 is a neutral. Okay. Now, when you reach here, you are going to factorize out. So since I have x squared, I'm going to factorize out x squared. So I remain with y minus 2. Then I go on this 2. I'll say plus x into negative 2y plus 4. I go to the next, which is going to be y minus 5 is equal to 0. Now, you know that from our quadratic equation, ax squared plus bx plus c equals to 0. So here, my a is going to be y minus 2. My b is going to be negative 2y plus 4. And my c is going to be y minus 5. In case you have a question up to that point, you may first ask. If you have a question up to that point, you may ask. Okay, now since we're okay, then we are going to go on and bring our condition. So our condition is going to be b squared minus 4sc is going to be greater than 0 for all real number. But I'm going to drop the equal. For reason is that our value for y should be above that value, not equal to that particular value. That's why I'm dropping the equal. Now here I'm going to have my b as negative 2y plus 4 squared minus 4 times a, which is y minus 2, times c, which is y minus 5, is greater than 0. Now, the next point I'm going to do is I'm going to open up my brackets. Here, you allow me that I open up from here, but I know at this level, we expect you that now you know how to open the brackets very, very well without any challenges. So those, you open it manually, open your brackets manually, but allow me that I go directly, I open here, I'll end up with 4y squared minus 4 times 2 is 8y minus 8y, then plus 16. Then minus 4, I'm going to first open up the two brackets. I'll have y squared minus 5y minus 2y plus 10 is greater than 0. So when I correct like terms, I'll have 4y squared minus 16y plus 16 minus, I open up the brackets, I'll have 4y squared. Negative 5 minus 2 gives you a negative 7. Then that negative 7, when you multiply it with the 4 outside, we shall end up with a plus 28y. Then minus our 40 should be greater than 0. Now, when you look at them clearly, you notice that this and this will cancel. So what are we remaining with? I have negative 16 plus 28. Negative 16 plus 28, we end up with a 12. So I'll have here 12y, then 16 and 40, 16 minus 40, we end up with minus 24, greater than 0. So the next thing you do, you continue. So now 12y is greater than 24, divide by 12, divide by 12, and therefore your y will be greater than 2. And now, that is what we call our range. When you go back and look at, I don't know whether we had this graph drawn, but I can show you. Let me first clear my board. I'm going to clear the board. I'm going to show you. When you go back graphically, we are going to try it, don't worry. When you go back graphically here, let me delete, and we draw that graph, you are going to notice that the graph we have been working with, 2x squared minus 4x plus 5 over our x squared, then minus 2x, then plus 1. That's how our graph looks like. When you remember, this is how our graph looks like. And now you can notice that at 2 here, where we have 2, it does not touch it. And therefore, that's why we say that our range for this value is y greater than all these values that are greater than 2. So that is how we obtain our range. Kindly let me know, have we understood? I want you now to let the theory, the algebra, and look at the graph as well. Have you understood the concept? You may first ask together, yes, okay, good. I can go back and members first finalize with the writing, okay. Yes, Bettina?
So for me, I had a challenge. I was kind of changing a device, but I stopped randoming and then I've not got the range. I'm seeing the Y, I don't know of the
Yeah,
range.
the range, we write it in terms of y. When you are, like we said, range means the y values. So what you do, cross multiply. After cross multiplying, this is the first step. Multiply through by y. Then you'll get something like this. But we are going to do another number. But the most important thing, you express your equation in form of y's. In form of y, such that you get a quadratic equation in terms of a y. So that's what we do. But we are going to look at another number in the same magnitude.
Then teacher, how about that equation of the b squared minus 4ac?
You remember from your quadratics in senior 5, you stated that for anything to be real, the discriminant must be greater than or equal to 0. Do you remember from quadratics? I don't know that it was
Yes,
term 1. Yeah. So that's why we brought in that to have, I think you called it for distinct roots. I don't know that you remember
yes.
those things. Now that's why we are bringing that idea. But I said the reason why we eliminate the equal to, greater than or equal to, the reason is that at that point, our graph does not touch. Our graph doesn't touch. So that's why we eliminate the greater than or equal to 2, because it is asymptotic at that point. Okay. Members, when you finish right, you let me know and then we continue. I don't know whether Favor we are on the same page. Husna, are we on the same page? Oh. Okelo Center, are we on the same page? Okay, when you finish right, Swabra, you let me know. Vicky, and then we continue. You just say finished and then we continue.
Yes, sir.
Yes, are we on the same page?
Yes. Very well.
Okay, okay. Yeah. Mm. Yeah. And this we are going to kill two birds at the same time. That is the beauty. These regions we get for your range, it means that now your curve here, even they may indirectly ask you, which region does your curve does, like the region where your curve doesn't lie. Now it means that any region below this line, your curve is not there. Anything less than 2, your curve doesn't lie there. So that's what called the region of restriction. The same way we are obtaining the range is the same way we get that region of restriction. It's the same way we get the region of restriction. Okay, okay. In case you wanted to put this range in a set annotation format, we write it like this: y greater than 2. That's how we represent it. Yes, Baswali?
Good morning, teacher.
Morning.
Teacher, for today I was unable to attend the lesson at first. I don't know why, but I'm confused somewhere here on the domain, but there I've been understanding, teacher.
The domain, we said you equate the denominator to 0, such that you get that value of x that does not make sense, that is meaningless. Such that when you are stating your domain, you exclude that particular value, because that particular value, there is not any output. Getting not yet?
Like x minus 1 is...
When you put it inside that function, you'll find that you get something out of 0. So we are trying to eliminate this 0, because here the function does not make a sense. It's like you starting a business where you don't expect any profit. So at that point, the function does not make sense. So we want to have that all the points which give or yield an output. Okay. So in senior 4, that's the region you called where the curve is meaningless. No, fully, we have said this condition of b squared, it is only used for the range, not the domain. A domain is another condition. For range, it is also another condition. Yes, so you get that difference between the two. Oh, why don't I first give you one more here? Allow me to give you one. Okay, no problem. Allow me to go here. No. Okay, let me first give you more. Allow me to give you another one at least. Take an example. Take an example. Because now, for that first one, I gave you when you had one value. What about when you do and you find that the values are more than? Take an example. I have y is equal to x squared minus 4 out of 2x squared plus 2x, something like that. So, can we also find the domain and the range? First find for me the domain at least, and then we see. Hmm. Jonams, I have not gotten what you mean. Mhm. Okay, x not equal to 1. Very good. So that is good, members. So here, but here be very careful because now I've seen someone has said 0, others are saying only -1. So here you state both values. Some of you are assuming, because remember, your domain, for the domain, we shall say that 2x squared plus 2x should not equal to 0. So when you factorize out, you have 2x and 2x plus 1 not equal to 0. So that means that 2x should not equal to 0, meaning x should not equal to 0. Or x plus 1 should not equal to 0, therefore x should not equal to -1. That means that here we shall have all the values of x apart from x when it is equal to 0 and when x is equal to -1. So now don't forget that value, whatever thing you are stating. In case you want to state it in the other format of using infinity and the rest of that, then here you have to be very careful. In other words, here you have to be very careful. Like you have negative infinity and this is infinity. And then you have 0 here, you have -1. So that means you are going to say from negative infinity to -1. I don't know what's happening, but sorry about that. So from negative infinity, from negative infinity to -1. Union from -1 to 0. Union from 0 to infinity. That's the meaning. So you have to be very, very careful because between -1 and 0, when you put in a value like -1.5, it makes sense here. Sorry, like -0.8 or -0.5, it makes sense. So in case you want to use this format, that is what you have to do. Okay, hope that is okay. Then the second one, now we are going to look at the range. Now, when we are looking at the range, I'm going to come again here and I look at my function. So we say to get the range, it's going to be a matter of us saying b squared minus 4ac should be greater than 0. So what are we going to do? We are going to solve. So you do your cross multiplication. So we shall have y into 2x squared plus 2x equaling to x squared minus 4. Open your brackets very well. 2yx squared plus 2xy equals to x squared minus 4. Collect like terms. 2yx squared minus x squared plus 2xy plus 4 equals to 0. Now x squared is common, have it out, and then you have 2y minus 1 plus our 2 of y, and then everything multiplied by x, then plus 4 equals to 0. Then feed in your a is 2y minus 1. B is equal to 2y. C is equal to 4. So once you reach at this point, you substitute accordingly. So you have your 2y squared minus 4 into 2y minus 1 into 4 greater than. So here, what shall we have? We shall have 4y squared, yes, minus 4 times 4 gives us 16 into 2y minus 1 greater than 0. So here we shall have our 4y squared, and we open, we shall have 16 times 2, which gives us the 32 minus 32y, then minus and minus gives us a plus 16 greater than 0, which you can first simplify by dividing throughout by 4. So when I divide through by 4, I get y squared minus 8y plus 16 by 4, which is 4, is greater than 0. Now, when you get this quadratic equation, we are going to go on and find that region. How are you going to do it? We are going to first have it factorized. And I do assume at this point, we know how to factorize. That's why factorization of quadratic equation is important. So kindly write for me, what is your factorized up now here? What do you get when you factorize out? Two numbers, you multiply, you get 4, you add, you get negative 8. That's what you need to keep asking yourself. So I'm waiting for members to tell us what is the factorized thing there. Are we getting anything factorized? Can it be factorized or it can't? You can let me know through the chat. Can we factorize it or not? In case it can't, then we use the bulldozer. In case it can't, we use the bulldozer. It can't, eh? Now, if you find that it can't, then we go on and use the bulldozer. Go on and use the bulldozer and tell me those two functions. But let me first confirm. Let me see why. Check out your bulldozer and see whether your values are close to these ones, these two. Check out your bulldozer and even those who have calculators, I know it can give you in whether your values are those ones. Dorcas has got those ones. You can use the calculator at this point. Then I'm going to draw this graph. I'm going to draw this graph at this point, and then I'll be showing you how this graph looks like when you draw it. When you draw it, y is equal to how it looks like. How it looks like, such that you know. 2x. Hope you are seeing the graph. Now, what are you noticing about this graph? I want you to look at it very well. Now, you notice that here at this point, one of the values you are getting, according to, kindly allow me to use points. Allow me to use the points. Allow me to use 7.464. Then here down, your line is 0.535, something like that, 89. Now, your range here, we are going to have two values. One value is going to be above. So for that one will be y greater than 7.464. Then you are going to have a value down here. And this value down is going to be y less than 0.53589. Kindly take note. Though I'm going to show you how we do it when we have those quadratics. But I don't know the members we are together. Now here, from the chart, here, your range is going to be y greater than 4 plus 2 root of 3. Then here for the down one is going y less than 4 minus 2 root of 3. That is the range. Now, in case members, they're asking which region, the region where your curve doesn't lie, the region where your curve doesn't lie, it is this region here that excludes the range. Now you get it. The region where the curve doesn't lie, it is this region here. So in case the question is asking the region of restriction, the region where your curve doesn't lie, it is this region. And for the numbers we are going to be drawing, we shall always exclude that region such that we know that in that region, our curve is not going to lie there. Hope that is okay. Kindly let me know whether it is very okay. Are we on the same page on that matter? Okay, okay. But I want to also show you why we let this one be greater than and this one be less than. How would you conclude? Because when you look at our numerical bit of it, you notice that our graph will not be able to show that this one is going to be greater than, this one is going to be less than. So you're going to allow me to say that here we have two roots. This is how we get it. And here pay attention. One of your values you got was 7.5 something. I'm going to assume that 7. Okay, let me write it one decimal place. It was 7.5. Then another value you got was what? 0.5 something. Was it 4? I want to show you how you come to conclude that here, this is, okay, let me be sure, 2 root 3. So this one, I'm going to use 4.5, then 4 minus 2 root of 3, I'll use 0.5. It is okay. Now, when I come here on my number line, I know this is where I have 0.5. 7.5 is going to be here. So when we are approaching to get such a region, I'll come here. I will draw I will find out the sign change, the change in the signs of my curve. So I'm going to get a region below 0.5, which I'll call y less than 0.5. Then I'm going to get a region between 0.5 and 7.5, 0.5 less than y less than 7.5. Then I'm also going to get a region above 0.5, something like that. Now, what does it mean? I have my function already that we have our quadratic function we factorized out. And that quadratic equation, if I recall, the one we have been factorizing, you'll come here. Allow me to first write it here. And I don't know whether you did inequalities. You might have done something like this in inequalities. Okay, then I'm going to go back. Now, this is the region y squared minus 8y plus 4 greater than 0. I'm looking for the region that is greater than 0. So what am I going to do? What I'm going to do, I'm going to look at the sign change. What am I going to do? I'm going to have a value less than 0.5. Any value less than 0.5. An example I'm going to take is take 0. 0 is less than 5. Any value, if I take 0 and I substitute here, I'll have 0 minus 0 plus 4 greater than 0. Then here I'll have the answer I'm remaining with is a 4, which is a, you notice that here I'm remaining with a positive. And you ask, is 4 greater than 0? So here, you notice that it will be something like a positive value that you remain with. when I put in a value between 0.5 and 7.5, an example here, put in a value like 1. So when you put in 1, you'll have 1 minus 8 plus 4. And then you ask, what is 1 minus 8 plus 4? You get a negative. So here, I'll have a negative. Put in a value greater than 7.5. An example, put in like 10. So you'll have 10 squared minus 8 times 10 plus 4. So you have 10 squared minus the 80 plus 4. You notice here you get a positive value. Now, what does it mean? Now, the region which satisfies, which gives us a value here that is greater than 0 is this region here and this region here. So your range will be the value y less than 0.5 and y greater than 0.5. Because they satisfy this inequality, they are greater than 0. Members, let me know whether we have understood that. Let me know whether we have understood that. Shadow says yes, got it. Others, are we on the same page? Yes, okay, perfect, since we have got it. Now, that's how we conclude that now our range will be y less than 0.5 and y greater than 0.5. However, now also let me also handle this at the same time. If you wanted to get the region where your curve doesn't lie, is the region that doesn't satisfy this kind of inequality. The region that is less than 0. So that region, when they ask, the region where your curve doesn't lie, it is this region. So in your graph, that is the region you mark. That within this region, my graph is not going to lie there. This region here. Check that greater than 0. Even if you check greater than 0.5, for you put any value, as long as it is between 0.5 and 7.5. Sorry, this is 7.5. Sorry, members. I did not say. This is supposed to be 7.5, not 0. Okay, thank you. I did not say. This is supposed to be what? 7.5. But I know we filled in the right thing. We filled in the right thing. Hope members have noticed this was supposed to be a value greater than 7.5. Or maybe I had written it badly. Maybe. Yeah. So, that is what you have to do. Members, should we do one more? Or you feel you have understood the concept? What do you think? Do you feel the concept is at one more? One more. Okay. Members are suggesting we do one more. Yeah. So we do one more. So one more. Allow me to give you which one? Okay. Let me give you this one. We have y equaling to 3x minus 9 into x minus 2 into x plus 1. So find the domain and the range. Find the domain and the range. Find the domain and the range. So I want everyone to first get the domain quickly before we go on to the range. One more. Okay, this is the last one. Okay, hope everyone has got the domain. Hope everyone has got the domain. Not equal to, okay, good. That is very true for our domain. So for our domain, our x minus 2 should not equal to 0 and x plus 1 should not equal to 0. So that means you are excluding 2 and you are excluding -1 for all your values of in the real numbers. Perfect. Then we go to the next part, which is the range. So the range, like we said, you'll always say b squared minus 4ac greater than 0. Now, what do you do first? You have to go on and first cross multiply. So I'll say y into x minus 2, x plus 1 equals to 3x minus 9. So this is going to be y. When you open up, you get x squared. Open up very well, x minus 2x minus 2. You first open up into 3x minus 9. So this will give you yx squared. X minus 2x is minus x, so minus xy minus 2y is equal to 3x minus 9. You collect like terms, yx squared minus xy minus 3x minus 2y plus 9 equals to 0. So at this point, you'll have y. Oh, sorry. At this point here, oh, okay, it is okay. You'll have your x squared and y. At this point here, I'll say plus, I'll have my x, then into negative y minus 3. Then I'll have here plus negative 2y plus 9 equals to 0. Then here your a is the y, your b is the negative y minus 3, and your c is negative 2y plus 9. So when we feed in that 4 squared minus 4ac is greater than 0, we shall have negative y minus 3 squared minus 4 into our a, which is y, and the c, which is negative 2y plus 9, greater than 0. So when we square, I'm saying a y squared. You allow me, I'm jumping a step, plus 6y plus 9 minus 4. When I multiply inside, I have negative 2y squared, then plus 9y greater than 0. So here we shall end up with y squared plus 6y plus 9. When I open up, I'll have plus 8y squared minus our 4 times 9, which is 36, minus 36y greater than 0. Then you collect like terms. Y squared plus 8 gives us a 9y squared. 6 minus 36 will give us a 30y, then plus 9 greater than 0. Now, you try to see whether it can be factorized out or not. So you try out and see. In case it can be factorized out, so much the better. In case it can't, then you have nothing to do. You can use your points. So I'm waiting for members to tell me what they are getting the factorized bit of it. Okay, people are getting from Lydian. I'm taking Lydian's answer, y minus 3 and 3y minus 1 greater than 0. Now, before I'm not going to take you to the graphical approach. Now, I want us to first do it here, the way it is. Now, to do it the way it is, I want to bring it to your attention. Always, for you to be able to get it very well, what you do, allow me to create another empty page here. What you do, draw your table, draw a table for you to pass those things very well. Draw a table such that you know. So I'm going to draw my table like that. whereby you have 3y minus 1 and then you have y minus 3 should be greater than 0. So here it means that your y, here when you solve, your y will equal to 3 and your y is equal to a third. That's what when you solve. So you can first draw a number line and you know that a third is here and 3 is somewhere here. Now you are going to look at the region less than, which is y less than a third. Look at the region in between, which is a third less than y less than 3. Look at the region above, which is y greater than 3. Now, after identifying that particular region, it means you are very safe to continue. Now, here, I can break it in this format. I don't want you to... Okay, may I can just put, if you want, it depends. You can put 3y minus 1, y minus 3, and then greater than 0. Or, for you can go directly and say 3y, in case you, I don't know whether it will come. Should I break it? Members, you first let me know. Let me show you the two approaches. I can first have 3y minus 1. I have y minus 3. And then lastly, I have 3y minus 1 and y minus 3. Alternatively, I can eliminate the 2 and I have 1. Which one do you want? Should we maintain this or we break? Tell me in the chat. Break or... Okay, members are suggest. One is saying break, do all. First, all. Okay. Okay, let me choose all. But for you, feel free to break. I know in some of the books you see them breaking. As long as here you are very good with multiplication. Now, any value less than a third, the quick value personally I can have is a 0 because it's less than a third. So what I do, I'll come here, I substitute. When I put in 0, I get negative 1. When I put in 0, I get negative 3. Then I'll say negative 1 times negative 3 is a positive. So here I'll write a positive. Then between a third and 3, I know in between here I have a 1. I put it here. So I'll have 3 minus 1, which is a 2. Y minus 2, which is a 1 minus 3, which is a negative 2. So here I'm getting a negative 2 times negative 2. Any value that is in between, it will give you that, a negative. A value above 3, I will take, which value? Maybe I take 4. So I will say 3 times 4 minus 1. Then after I say 4 minus 3. So 3 times 4 is 12 minus 1 is 11 times the 1, which is a positive. So here I'll get a positive. Now, since we wanted values that are greater than 0, then therefore we shall conclude that which one gives us positive? This and this. So that means that now we shall conclude and say our range will contain all values that are less than a third, all values that are greater than 3. Now, if they ask you the region where your curve doesn't lie, then you just come and say, yeah, this is the region that doesn't satisfy. You take that. Members, is it fine? Hey, if you want to, you break. Now, in case someone was breaking, in case for you, you wanted to break, this is what would have happened. For you, you would have said 3y minus 1. From there, you go, you say y minus 3. From there, you go and you say 3y minus 1 and y minus 3. For person who's breaking, now after there, you say, I get a value less than a third, say 0. When I put in here, I get a negative. Any value between a third and 3, say 1. Once I put here, I get a positive. Any value above 3, I get a positive. Y minus 3, any value, say 1, you get a negative. Any value between a third and this, I will get a negative. Any value above that, I will get a positive. So negative, then here, since you are multiplying, negative times the negative gives you a positive. Negative times the positive gives you a negative. Positive times the positive gives you a positive. So therefore, you conclude that your range has that and has that. That's how you do it. Okay, now in case you had gone on the graphical bit of it, this is how it looks like on the graph. On the graph, oh, what was the function? the graph, in case you wanted to visualize it on your graph, you'd have had something like this. Y is equal to 3x minus 9 over, it was, what was it? X minus 2, x minus 2, and x plus 1. You'd have had something like that. So you'd have noticed that your range, surely, here at this point, it is above that. That's why we said y greater than 3. And this point here, which we obtain as y less than a third. So it will be this region. In case they ask us the region where the curve doesn't lie, it is this region here. And now I'm not going to handle region where the curve doesn't lie. It is the same procedure for finding the range, but you get that one that is less than, or that one that doesn't satisfy the inequality. Okay. No, Jonams, that is just by luck. That's just by luck that they may coincide, but it's not true. It's not true all the times. Yeah. And never use that kind of approach. Okay. I feel I have finished to handle that. Now, what is the, okay, unfortunately, my time, I don't have a lot of time, but tomorrow, we shall look at just one more concept and then we start on sketching. But why don't I give you some 2 numbers to try out to find a range and to find a domain. To find a range and to find the what? The domain. To find a range and to find the domain. Only 2 numbers for you to try out. So the first one I'm going to give is going to be which number? Which number? Which number? So this is the first one. Y is equal to x minus 3 out of x minus 1, x minus 4. Then number 2, we are going to do y is equal to 4x minus 10 out of x squared minus 4 minus 4. Yeah, at least those ones, they will give us a good picture on what to do, Yeah, but I know, but let me give you 3. Y is equal to 2x squared minus 8 out of 2x minus 5. Those ones will be enough. And once, I want to tell you that once you master those things we have looked at, tomorrow, we shall just do one graph and you feel that you have understood everything. Make sure that whatever thing we have been looking at, you have understood it very well. Make sure you have understood it very, very well. The domain will always tell you that now when you are sketching your curve, go, don't stop. So we shall start from there tomorrow. Let me wish you a good day and let's practice and master these ones. And always, please, like I've told you, always go back and look at the syllabus books. I sent those books in the group such that you have a check whenever you are learning that this is what they require in the syllabus. You go back, like though you see even for this math, for whatever thing here, go back and ask. Now, like here, you go back and ask yourself, is whatever thing I'm learning on the syllabus, you look at the areas that have been emphasized. Now, like last time, like we are looking at exponential, you ask sketch exponential and logarithmic. You ask yourself, do I know how to sketch such graphs? Did we look at them in class? Did we look at limits, the concept of limits and the derivatives? So you keep on checking. So such that you know that whatever thing you are doing is on syllabus. We looked at the Macrini's theorem series, and now we are here. So what are we remaining with here? I know now we have covered the intercept. We looked at asymptotes, we have looked at range and a domain. So we have looked at how we geometrically I've showed you, algebraically we have done. Now we have looked at the concept of increasing, decreasing, concavity, we looked at turning points. Now what is remaining? We are going to look at the differentiation and sketching of the curves. The moment we finish, and maybe the last bit I will show you are those who have laptops, computers. Now I will tell you to have this software also on your gadgets, and then I will show you how we can use our phones to graph them. So that will be the last bit of it. How we can use our phones, those who have laptops, to graph them. That will be the last bit of it. Otherwise, thank you so much for attending. Have a lovely day.